Right, good afternoon, everybody. Welcome to the ICAIR live virtual tour. My name is Matthew Gilbert. I'm the director of the ICAIR facility. I'll be joined today by my colleague, Simon Tait, who heads up the National Distributed Water Infrastructure Facility, which is a part of the ICAIR laboratory. Just to give you a little bit of heads up on the housekeeping, we're not going to stop the tour for questions, but we do ask you to use the Q&A facility in Zoom. So you can access that by moving your mouse to the bottom of the screen and then add as many questions as you want. And there will be 10 minutes or so at the end of the tour for us to pick up those questions. So first of all, I just want to say a few words about ICAIR. First of all, where is it? It's actually co-located with the Factory 2050 facility out on the Parkway. There's several engineering faculty buildings there as well now, and you can see where ICAIR is relative to those on the slide. In terms of the funding that underpinned the ICAIR facility, we actually had funding from the European Union and also from EPSSC through the UCRIC initiative. And we also had co-funding from the university. What's it all about? Well, in a nutshell, we're focusing on physical constructed infrastructure, and we're trying to basically move technology forward in that area. So you can see our sense of vision to promote the intelligence, resilience, and resource efficiency of physical infrastructure, benefiting people and planet. In terms of areas of interest, it's a very broad spectrum. So it could be existing assets, pipelines, bridges, buildings as well, looking for ways of inspecting and repairing those buildings. It could be using data from sensors on instrumented constructions and trying to use those that sensor data to inform the management. Also looking at new ways of constructing infrastructure, also assembling, deconstructing, and also rehabilitation of existing infrastructure, and also reconfigurable and smart infrastructure. When we set up the facility, we were very, very keen to see this as effectively a catalyst and a conduit for expertise from a range of disciplines. So I think many of you on the webinar today potentially have important skills that you could potentially bring into our work at ICAIR. So we have clearly the civil engineering disciplines, water engineering, geotechnical engineering, structural engineering, and so forth. But we also have, people who are working on new algorithms in AI, big data, and so forth, and robotics, and many, many other areas potentially feed in to deliver benefits to the wider world. And we're closely working with both small and medium-sized industries and also with our colleagues at AMRC and Nuclear AMRC. In terms of the actual facilities, it's basically two parts. We have one side of the building is the Intelligent Infrastructure Laboratory, which is effectively what we informally call the dry side. It's an above ground side where we've got a very flexible space for doing structural testing. And the scale means that we can actually potentially test real scale components of structures that we're not able to do in our facilities in the main campus. And two main areas there: legacy infrastructure, so looking after that in terms of clever ways of inspecting, managing that infrastructure, and also new infrastructure using digital manufacturing techniques, for example, and other techniques in order to design and construct low embodied carbon infrastructure. And I'm going to hand over to my colleague Simon Tait, who's going to just talk you through initially the National Distributed Water Infrastructure Facility, and then we'll move on to the live tour.
Okay, thank you, Matthew. Matthew said, this slide here shows you part of the National Distributed Water Infrastructure Facility, which is part of ICAIR. This picture here shows the facility when it was brand new. and you'll see a difference when we start the live tour in a couple of minutes' time. So the key part of infrastructure we have in the laboratory is a very, very large testing tank. So it's 45 meters, 6 meters deep, and 5 meters deep and 6 meters wide. This allows us to look at buried potable water supply systems and also pipes and assets that are buried that supply sewage and drainage services. So if we go from this nice, clean, empty image to the main facility now, hopefully we'll see the difference. So you now see the facility from the other side with Ed. So you can see the large testing tank now is divided into two with the large green dividers. On one side, we have a full-scale buried sewer system. So you can see the manholes with the groundwater levels and the black pipes that pop above the surface. On the right-hand side, you can see buried water supply pipes. So to give you some idea of the depth of the facility, the previous slide gave you a nice clean facility with no sand. We now have about 2,000 tons of sand in the facility. So you can see that it's still got the 5 meters depth, but we've now got a test cell filled with the green stop logs, and we've filled that with, as I say, a full-scale sewer pipe and also potable water pipes, the plastic pipes that we can generate pressure transients and put forces on it. The yellow beam that you can see allows us to put soil surface loads on these buried infrastructure. So we can put road loadings, lorry loadings. We can also put accidental damage loadings, that people actually drive through the soil and hit the underground infrastructure. So Ed, do we want to start walking our way through the facility? So as well as the tank itself, we do various sorts of interesting things. We have damaged pipes. Also, we have perfect pipes as well. So yeah, a damaged pipe there. That's a pumped sewer main with some nice perforations along the bottom of it for the wastewater to escape. And we move to our nice plastic Perspex perfect pipe with perfect joints. And we use this pipe to test our understanding of turbulent flow in pipes and also sensors as well. So if Ed maybe looks down a bit, you'll see the pipe section that we've taken out, and the black housings there are for fiber optic based and pressure sensors to be placed in the base of the pipe. That will then be replaced in the pipe rig, and we'll be able to test pipe flows with these novel sensors at a full scale. If we start walking down the lab itself, you'll see behind the sort of fences here is our sort of reservation for robot testing. And in here, we have a large program grant here led by Kirill Horoshenkov, and it's looking at developing autonomous sensors to work in pipe systems. So we've got a full-scale sort of pipe system here with a manhole, different types of pipes that allow our robots to wander about in safety without getting lost in the real world. Keep walking up again. You'll see we have large black pipe loops on the right-hand side. That allows us to look at pressure transients and allows us to simulate hundreds of kilometers of pipes in the facility itself. And if Ed maybe moves along and maybe walks into the test bed itself, give you some idea. So it's 5 meters of sand that he's now standing upon. And we've buried water supply pipes, and now he looks at our buried sewer as well. So it allows us to test full-scale facilities. We put all this material in, we order a contractor in who turns up with his excavators that are lifted off, and then we take all the sand out, put it out through the side doors, and then it gets taken away either for disposal or back in once we built the system in the test facility itself. Right, so shall we start moving towards back towards the top end of the lab itself? So more pipes for testing sensors. These are acoustic sensors that get tested in the orange pipe. Keep on walking, Maybe turn to the left here, Ed, and we can sort of see the top end of the water supply pipes, and that gets linked to a pumping station. So if Ed just turns to the left a bit, right, left a bit more. Oops. And you see one of our pumping stations. So this replicates the flow rates and pressures that you'd see in a water supply system. The other thing we can do with these pumping stations is we can generate transients, and the two orange sort of bits in the side allow us to heat the water to particular temperatures. So we can look at temperature dependent processes and heat transfer in soils and things like that, all at a full scale, which means that, if you take the results, tend to be high quality, and they also are useful when you're talking to end users to convince them that, everything's at a full scale. So all the sort of fluid parameters such as Reynolds numbers are appropriate. And also we look at sort of heat transfer, acoustic processes at full scale. So there's no need to scale measurements or the physical processes. Right, Ed, shall we walk up towards the top end of the lab? So as we walk up to the top end of the lab, the lab itself is fed by two large tanks of water, which are above Ed at the moment. These tanks contain 500 tons of water each, which is why the roof beams are quite strong. And from the base of these tanks, we have a sort of flow control system that feeds into the test bed itself. So the flow control system, we have flow meters, automatic control valves that we can control automatically from a remote computer. We also have logging systems. So we can program steady flows that represent rainfall, runoff rainfall events with a nice hydrograph, and also unsteady flows within the pipes themselves. So these pipes feed the test bed itself. And if you just want to look down the lab again, and we've got two sides of the test bed, and on the right-hand side, we have our sewer network, and that gets fed from these header tanks that allows us to simulate, what would happen in a sewer during a full-scale rain event, or if we want to test novel instrumentation, we can test that at repeated steady flows and with repeated flows during rainfall events. Because one of the experience you have working in urban drainage systems is field work's very difficult, because every time you want to do a field test, it never rains. But here we can generate the rainfall events in a planned and consistent way. Okay, Ed, do you want to sort of move your way through the building, and we'll start to look at the Intelligent Infrastructure Lab.
Right, so thanks, Simon. It's Matthew again. We're now moving into the Intelligent Infrastructure Laboratory. The first thing we can see is actually a modified schools outreach bridge. So this isn't a pure research project. It's more an outcome of a research project, and then actually using that to demonstrate in a small scale one of those outcomes. So in this particular project, what we were looking at was using so-called layout optimization to try to identify minimum volume layouts for, in this case, long span bridges. So if you, for example, imagine the Humber Bridge, it's a long span suspension bridge, just short of 1.5 kilometers in span. It has vertical pylons and it has very large main cables. Using mathematical optimization, we found out that actually that was far from optimum if you consider gravity loads alone. And actually, in steel, you can span more than twice as far if you use this split pylon arrangement you can see here. And so this is an area that we're looking to advance in the future with colleagues from the universities. Also looking at interaction with wind, which is clearly very important for cable supported structures of this sort. But this is just a sort of a physical manifestation of some of the work we've done in this area. Okay, Ed, if you just start walking through the lab a little bit. If you look up, you can see we're actually in a single height area of the building. Above the where Ed's standing now, we actually have a sort of a workroom space. And so for people who are spending time doing experiments, there's also desks and the like for that kind of activity. So in this single height area, we've got it's basically a sort of a small scale test area. What Ed's looking at now is actually one of the test setups we have in an EPCC funded project joint with Leeds and Imperial. Actually got a part of a skew masonry arch bridge in position there. Interestingly, these structures are clearly have been constructed for millennia on the UK railway network. I think around half the bridge spans when you travel on a railway are masonry arch construction. Yet we don't really understand fully how they work, particularly skew masonry arch bridges. And so, as part of this project, we're trying to build that understanding through experiments, but also lots of mathematical modeling as well. And the aim is to reduce the likelihood of needless strengthening, demolition, or actually it's been the media quite recently, infilling of these structures, where I think national highways ended up infilling, we believe, needlessly quite a number of masonry arch bridges. If we understand them better, then we can make more informed decisions about what maintenance regimes are needed and whether those structures are safe for the long term. In fact, another sort of area, we just started a project actually a couple of days ago where we're using stone masonry as a low embodied carbon construction material. So clearly stone masonry was used a lot in the 19th century and at the start of the 20th century, but has fallen out of fashion. One of the benefits of stone is that it can be quarried if it's near to a site and transported and then erected with very, very low embodied carbon compared with, for example, concrete, where that process is carbon intensive. And if we're going to reach net zero targets, then this is something to look at. Ed, if you just spin to your right, I think is there a computer monitor with just a bit further? Somebody in the way of the computer monitor. If you just ask Serena to just step out of the way. Yeah. Okay. So this is actually from a previous test on a square span, and what we have digital image correlation techniques where we're using those methods to actually get a 3D profile of the response. As I understand it, understanding the 3D response to masonry arch bridges is incomplete, and we're doing rapid turnaround small scale tests to try to help understand that. Okay, we'll leave Serena alone now. If we move down the lab into the double height area. So this is the main area of the laboratory. If you look just down on the floor, you can see lots of dots, and those dots are basically places where we can insert threaded rod for anchorage. So each of those anchors can take a force of just over 30 tons. And what we can do is we can set up a test apparatus in a very flexible way using this strong flow. I think there's 288 of those anchor points. And the double height area is 24 meters long. So we can actually test specimens up to 24 meters in length, which is a real scale capability. If you just look on your right, there's actually a more modest scale structural element that's been tested recently. This is actually a reinforced concrete slab where loads have been applied from below, pushed upwards, and actually we've got a punching shear at the center. And you can see we've actually got a yield line pattern. If we just zoom out, Ed, it's like a sort of a cruciform. And the speckle pattern is again to allow this DIC technique to be used, so we can get a good three-dimensional indication of how this is behaving three-dimensionally. So we can compare that with computer models very, very nicely. In this particular case, we're exploring the use of a digital manufacturing technique, laser cutting. And so rather than using conventional rebars in this particular slab, we've actually got laser cut steel, which has quite a strange geometry, but it's a geometry which is an outcome of computational optimization. And we can use optimization to potentially significantly reduce the amount of steel that's required to reinforce a structure like this. So in this particular case, where we have the predictions, it's a question of actually doing the test to see how closely those predictions match the reality here in the lab. Right, if we just zoom out, Ed, and perhaps just walk down the lab a bit, as you can see on your left, there's a steel concrete composite beam. It's actually quite a short beam. We've mostly been testing significantly longer beams than this, but this is a short beam for a shear test. We're going to be loading this very close to one of the supports. So in this particular case, we don't need a very long beam to do that shear test. In this particular case, we're using two meganewton actuators, and we're going to basically pull down and apply a vertical downward force onto the specimen. In this particular case, we are taking advantage of at the bottom of each of these actuators. If you look down on the feet of these actuators, you can see we've got 4 bolts. So that's 4 times 30 tons. So we've got 120 ton capacity on each of those. And so we can pull down basically with around 240 ton force. If we have bigger base plates, actually, we could apply an even bigger force. In the case of this particular specimen, it's a project that also involves laser cut steel with a local company, formerly Metlays, now Unipart Construction Technologies, working closely with them and also with the Manufacturing Technology Centre, one of the catapult centres, on the efficacy of using laser cut steel to obviate the need for all the steel fixing that you typically need in reinforced concrete construction. And the steel here also acts as permanent formwork. Then the next step is to see whether we can actually then use laser cutting to reduce the amount of steel so that we can have a more climate-friendly, lowering embodied carbon solution. Okay, Ed, if you just carry on walking towards the back of the lab, and then I think if you just and then swing to your right, so you keep walking forwards, forwards, and then spin so you can see the timber trusses. So there's 2 timber trusses that you can see. One's actually in position that's going to be load tested with those green actuators, and we've got the sort of the blue goalposts that are providing the reaction. And then you can see it's going to be set up shortly. And then on top we've got a sort of sister truss, which you can see has quite a different geometry. And this is another example of us using structural optimization techniques to take out material. The structure below that's in position is a Warren truss, and it consumes significantly more material than the optimized structure below. In fact, the optimized structure above, should I say, the structure above is 60% of the amount of material as the structure below. And yet, if you use, for example, laser cutting again to form the steel plates at the joints, there's very, very little overhead in making lots of different geometries rather than just having a small number of repeatable geometries. So one of the big areas is looking at how digital manufacturing techniques can potentially allow us to deliver more bespoke, optimized structures and sort of move away from the focus, I guess, of the late 20th century, where we were typically focusing on simplifying everything, but at the expense of material efficiency, given the drivers that we currently have, the climate emergency. So those are some examples of new construction. We also have had in the lab examples where we've got bits of existing infrastructure where we're monitoring those with various different types of sensors in order to get a better understanding of the way that those are going to carry on working into the future. Typically, with infrastructure, we're talking about long design lives. In case of bridges, we typically have a 120-year design life. So we want to make sure that we understand how those elements are going to work into the future. We've seen in the media in the last couple of weeks that rack concrete in schools and hospitals and the like, where clearly the lifespan of those structural elements has not been as long as originally envisaged, and leaves us with a problem. So I think that completes my whirlwind tour of the Intelligent Infrastructure Laboratory. I think we'll probably, if we spin back then to the presentation, and we'll have a look at the Q&A and see what questions that you might have.
So if anyone would like to use this opportunity to ask questions of Matthew and Simon, please enter them into the Q&A chat available at the bottom of the webinar. At the moment, we have no questions, so if you're in quickly, you'll get your question answered quite soon.
I appreciate it was a lot of information that Simon and I kind of tried to impart. So if you're feeling a little bit sort of bewildered, then that's quite understandable.
I guess for me, a question might be, what are the opportunities for people to get involved in other disciplines within the university?
Certainly, in the water testing facility, we've people from mechanical engineering, automatic control in projects already. We work with SMEs, so there are opportunities for us to collaborate with people or to help people put bids together to allow them to use the large scale of the facilities to look at issues themselves. So we've both Research Council funded projects in the facility and also more commercially focused projects as well. So we're always very happy to help people if they've got an idea that they would like to test in the facility itself. And I think that's for both sides, the water side and the structural side.
Yeah, I would agree with that. I mean, one way of seeing the facilities that we have is a sort of data generation machine where this is real data. You don't need to synthesize your data to get your big data algorithm up and running. You can actually get real data with all the complexity of the real world, and potentially get more useful outcomes.
Okay, and another question, perhaps in terms of sort of external partners that you work with, would you be able to give an indication of the types of companies that you engage with through the facility?
Yeah, in terms of the facilities as a whole, we have a steering group that has local and national companies. So it could be infrastructure owners, water companies, contractors, companies like Lang O'Rourke, consultants like Arup, Jacobs. So lots of big organisations are helping us to sort of decide on the future of the centre. But then when you move down to sort of project level, most of our projects have got industry partners. For example, the Masonry Arch Bridge project that I spoke briefly about, I think that has 15 industry partners. So Network Rail, National Highways, Canal and River Trust, Arab, AECOM, many key stakeholders, and clearly having those stakeholders on board means that the likelihood of the research being relevant to them is that much greater. But also have had quite a focus, particularly in the early days of the centre, on working with local companies. That's part of one of the conditions actually of European funding that we did that, but lots of useful collaborations, of which the Metlay's one is just one example. So that started off as an EIDF assist, but has turned into a long-term, very, very valuable relationship, mutually beneficial relationship between the university and that company.
Okay, so there's a couple of questions coming in now. So the first question was, we're a group that specialises in software testing. Do you have a need for software testing, such as model-based testing or search-based evolutionary testing?
Right, Anthony. Yeah, I mean, as well as the physical testing here, particularly with infrastructure, a lot of deterioration modelling or failure modelling now is done with data-driven approaches. So we do like to link up, physical measurements or physical data collection to develop more physically based models that certainly infrastructure owners can use to assess when particular parts of their infrastructure can fail. And certainly in the water side of things, our infrastructure networks tend to be very large. A typical water company will have 60,000 kilometres of pipe. Network Rail, I think, has about 100,000 kilometres. So our understanding of how elements fail and how that can be taken into a sort of more modelling approach to put it to a national infrastructure provider is something that we're interested in. Who's best for inquiries? Just contact Matthew or myself. And we'll sit down and have a chat. It may be that there are a whole range of academics that use the facility, so it may be that a more fruitful conversation is not with the two of us, but we'll put you in the right direction. Also, we're happy for our technical staff to discuss your technical needs and help you with some ideas that you may wish to develop. Opportunities for engineering students, yes, provided we do the risk assessment. We've had MSc students here working on sort of quite nice, large pieces of equipment and kit, so it gets them a bit closer towards reality and being able to collect real data from full-scale bits of infrastructure. So yeah, we're quite happy to look at engineering students doing short projects, MSc, undergraduate projects, or industrial placements here as well.
Yeah, we have had, for example, students go through the student job shop who have been helping with particular experiments when there's a particular need, and that can be for 3 or 6 months or generally short periods. In terms of industrial placement years, we don't have reserves of funding to effectively to do what, for example, an engineering consultant would be able to provide, in general, I guess, Simon.
But we'd probably maybe look at the idea that if there was an industrial partner that wanted to do some testing here and there was an opportunity for a student to work with that industrial partner, then yeah, I mean, as I say, one of the concepts of the facility was to be collaborative and flexible. So, come to us with your ideas and we will try our very best to make that idea be realised. Because the whole facilities were designed to be flexible. So the big tank itself has got craneage, access, and it's got flexibility for us to build a whole range of different types of underground infrastructure.
Yeah, it's a good point. If you contact us, and it might very well be that we have an industry partner who may be very receptive if there's a fruitful line of inquiry.
So if there's no further questions, then we'll close this session. And thank you for what last question come in. Okay.
Okay. Yeah. Thanks, Inshira. So hopefully you'll understand where we actually do the work, if that makes sense. Not that we've disappeared all the time.
Yeah. Okay.
Thanks, Inshira. Well, thanks everyone for joining the webinar today.
Okay, we should say this has been recorded, so we will make this recording available as well for future use as well. So thank you very much, everybody.
Okay.